applications track of the hackathon. So without further ado, let's welcome Howard and hear from him.
Thanks, Devesh. Hi, guys. As Devesh mentioned, my name is Howard. I am a former I'm a Berkeley alumni, and today I'm going to be talking about Aleo, which is a new ZK-L1. To give you some background context, Aleo itself was actually originally developed as a research paper called Zexy. Zexy itself was published back in Oakland 2020, and we started the company shortly thereafter and built out the production implementation of this paper. And so along with my co-authors, we started the company back in 2020. We're currently in testnet 3, and I'll talk a little more about that towards the end. But to give you even a framing of how things work, I want to really cover two areas today. The first is on how to build a ZK-L1. And for those who are not familiar with ZK or L1s, zero knowledge is ZKPs are a fundamental primitive, which I think is covered already extensively in this curriculum. But in terms of L1 protocols, we have existing protocols like Zcash, which offer you private payments. But private applications are still a very new domain for ZK. And so having that generality and a VM model that can support full generality is now just starting to become practical. And so I'll talk you through and walk you through kind of how we designed that. The second part of this talk is really going to be kind of going concretely into what we've built and giving you a preview into kind of what the language looks like, applications that can be on there. I'll show you a live demo as well, just so that we can all get our hands wet here. But with that, let me just jump right into things. So, first off, ledgers have become a very have become a foundational surface for a lot of different types of applications. We have things like micropayments. There's now trade and finance, NFTs, domain name storage, bridges. And as you can imagine, this has led to a lot of interest in using the technology, not only to chart new domains, but also to scale up the number of users on it. And we run into some interesting problems here. And before I jump into these problems, we should first talk about how ledgers work. So on a high level, the way that a ledger works is through what we call checking by re-executing. In very plain English terms, a user submits a transaction which contains three things. There's the application itself, some input for that application, and a signature. Effectively, the user says, I want to run this program with these inputs. And the nodes on the network say, all right, let's go ahead and do that. As part of that, they all re-execute the same piece of computation given a transaction. And assuming that the execution was correct and the signature was valid, meaning it was authorized, then the state for that application is updated. And this is fundamentally how every L1 works under the hood. But let me talk you through what are some of the challenges. So the first is that this model of ledger re-execution hurts scalability. And what I mean by that is that every party must re-execute every transaction to ensure the integrity of the ledger. So if we take, for example, like ETH1, there was about 3,000 nodes in the network. They were doing, let's just say modestly that it was 5 seconds of computation per block. In reality, it's usually 5 to 10 seconds. But at 5 seconds, we're already at 15,000 seconds or 4 hours of re-execution for each block, which is quite a lot of work that is being done that's, quote unquote, wasteful. And, by that measure, we think that this is a fundamental limitation to existing ledgers, is that this model of re-execution limits the scale of the network and its ability to actually hit high throughput. One of the other issues, of course, is that ledger re-executions hurt privacy. And so, one of the primary strengths actually of a ledger is the fact that all the information on there is public. But the challenge is that because it's all public, anyone can see your account, they can see your input data, your program state, your output data. The example that I like to give is to say I owe you some money and I want to send you some money. If you gave me your bank account number, knowing your bank account number reveals nothing to me about how much money you have, how much money you spend, how much money you make, where you spend it, where you work. I don't learn any of these details about you, and I can't really deduce much, in terms of your financial history other than the bank name. And but if you were to give me your Ethereum address and have me send USDC to you, you can imagine that suddenly I can track you very clearly. I can track not only how much you have and how much you spend, but I can also opt into seeing effectively your history, your transaction history for the rest of time, because now that I have your address, I can just continue to check back in on your account and look and see what you've been doing on there. And so, as you can imagine, this starts to open up Pandora's box in terms of analytics and also in terms of monitoring, depending on how you want to look at it, half glass full or half glass empty. But the fundamental limitation that we argue here is that this design itself is not compliant with real world applications that we expect. When you look at how the Web 2 itself was shaped, you have this server and clients, and servers are responsible with keeping a partition for privacy of their users, of these clients. And in Web 3, we've replaced the server with a ledger that everyone can see. And so, I think that it's fundamentally a part of the journey that we need to introduce the notion of privacy into every application if we want this to be used in the real world. And so we built Aleo. Aleo itself stands for Autonomous Ledger Executions Off-Chain. It's a decentralized ledger, and it enables users to execute programs off-chain and then finalize the state transitions on-chain. Under the hood, we offer scalability, and we define that as thousands of transactions per block. We define privacy as transactions revealing no user data for the executed program. And lastly, that this protocol is succinct, meaning that transactions can be validated in poly-K time. Transactions are roughly a kilobyte in size, and they take under 50 milliseconds to verify. And we think that this is a very acceptable bar to meet in terms of practicality. And in terms of what we've defined as the developer environment for programs, we've offered extensibility, meaning user-defined programs that are isolated. So they're sandboxed so that you can't have malicious programs affecting honest ones. And also allowing IPC, inter-process communication, that functions should be able to call other functions from other programs on this network. And so we've been very deliberate in providing what we expect as like the kind of typical runtime environment that a developer would want when they're building applications. So in order to walk you through this, I think the best way to kind of start is by lifting from something that I think many folks may be familiar with, which is the account model, and using that model to design this new paradigm, this new type of ZKL1. Just to remind folks, in the account model, the ledger tracks each account via global state. So what I mean by that is that every account is an address, and every address has the ability to create transactions, which contain in them some address to reference, some value, some data, a possible fee, as well as a signature authorizing this. And when it gets included into a block, this goes into global states. And what every node does is they proceed to pull up that account from storage. They perform the state transition that the transaction asks for, and the balance and the storage of that account is updated to reflect the new state. And you may wonder, what's the problem with this design? Well, let's first say, in terms of pros, it's simple, right? Like it's easy because developers can just coordinate the state for multiple parties on chain. But one of the challenges, of course, is that this has low scale, and the dual of low scale is high fees. So when you have a large number of unconfirmed transactions in the queue, it can cause these major spikes in network fees, hundreds of dollars that you would have to then spend in fees just to get your transaction, which could be far more minuscule through. And we've seen this in practice on Ethereum over the years, several times during CryptoKitties boom as one of the earlier ones. There was also during DeFi summer. People spend a lot of money in order to get their narrow sliver of transactions through, because a system like this does not have significant throughput. And of course, as we've already elaborated many times, there is no privacy in this model. It's very difficult to bake privacy. And why? Well, it's easy to take something that was hidden and reveal it. It's much harder to first reveal something and then try to hide it later. If the cat's out of the bag, it's out of the bag. And so, this is one of the challenges with this design, that it's public by default. And we want to kind of turn it on its head and make it private by default. So the first way to attempt this is to say, why don't we start by extending the account model? And the first intuition that you might have is to say, why don't we build private smart contracts? And this is absolutely the right intuition to have. And let's put together a straw man based on what we've just talked about with the account model. So Let's take that transaction, that object that we just saw on the previous slide. And, first just taking a look at it, it seems like, well, the value is something we don't want to reveal to people. We certainly don't want to reveal our data. And so why don't we commit to the value and let's encrypt this data? Just by doing this alone, we've already provided some level of data privacy because that information is no longer publicly visible on chain, right? And instead of using a signature, we need to use a proof now. Why? Because in order to attest to this transaction being correct, without leaking that data, you need to prove that the commitment and the encryption was done on the correct data in the correct way. And so a zero-knowledge proof here is extremely useful for attesting to the state transition and its encryption in global state. The second part to this is to say, well, remember that on chain, we're storing your account. And you may wonder, well, how do you take that and make it private? So this is just the first step we need to do. The first step is to say, why don't we, take that balance, turn it into a commitment as well. For that piece of code, well, we should probably turn it into a predicate. So we make it some NP statement and we canonicalize it in some mathematical form. This way we can actually reason over proof statements about it. And lastly, for storage, we should encrypt that storage so that, there's no way for people who are just perusing the network and looking on chain to be able to see your personal data on there. And, this is kind of that first step in this model. Now you may be wondering, well, how do you prove that the encrypted stuff is correct via consensus? Since now the network can't see your data, how do you know that the program is executing correctly? And this gets to the heart of the value proposition for zero-knowledge proofs. It's that instead of just authenticating or providing integrity on data itself, it can provide authenticity and integrity on logic. And that's something that I think is incredibly powerful here. And so what we actually are doing is designing a model where this whole system end to end is encrypted and committed to. But what we're using is a zero-knowledge proof, as you can see in the bottom left corner there. We're using a zero-knowledge proof to basically account for the actual transitions that are happening. And the network is no longer producing the executions. It's validating the proofs in order to believe that the encrypted data transitions you're going from, previous state to new state is actually valid. And to show you kind of how this looks under the hood, let's expand this concept of this proof and say, what is the statement that it's even arguing for? Well, on a very high level, we can say that you're providing as input the predicate, so the code that is actually going to be executed for this program that the developer deployed, as well as the existing state. So you're going to provide the current balance that's committed to, as well as the current storage, which is encrypted. And just as a kind of an intuition building model, you can think that in this proof, I'm going to open the commitment and I'm going to decrypt that storage. So I can now, inside of the zero-knowledge proof and inside the circuit, reason about the actual unencrypted underlying data and perform logic on that natively. And what we're going to do is we're going to claim as an output that there is some new state which has a new balance that's committed to and some new storage that is encrypted. And you can imagine, inside of this circuit, once you've executed this predicate on these decrypted inputs, you can now, get some new output and then subsequently commit to the balance as part of the new output and encrypt that new output and put it into storage. And so, naturally, you're kind of taking this old data, you're massaging it with some logic, and then you're putting it back on chain as some new logic. And the circuit now kind of concretely, it's checking one that values conserved. So we need to open these and make sure that, well, first off, left side and right side sum up to the same balance. We're not minting money out of thin air, that values conserved. But then secondly, that the program predicate is satisfied. So we put as input all of those things that I mentioned in terms of the old state and new state, as well as their openings. And we effectively compute that predicate and make sure that it actually checks out for this given assignment. And so we have this notion now of being able to execute arbitrary logic inside of proofs. And this is what allows the network to then take this proof and just blindly accept the new state transitions if the proof says true. And this is fundamentally kind of that first intuition in terms of how you want to design this. Now, I've spent a lot of time convincing you that this model is a good model, and now I'm going to tell you why this doesn't work. So the first point, which some of you may have already noticed, is that one of the challenges in this design is that we are asking for a network of random participants at random times to be able to come online and interact with the same program. And as you can imagine, this model, as you just saw, requires ingesting the entire state of the program in order to perform a state transition. And so it's a very inelegant solution. Why? Because there's no concurrency. So if a person comes, like person A comes and executes this program with transaction 1, well, when person B comes and executes the same or their own transaction, they're going to be proving an outdated state. Why? Because the first person took the previous state, executed it to perform the new state, and the second guy is still using the original old state and then performing a separate and it'll look like a double spend, right? So this is fundamentally one of the challenges in this design, is that you lose concurrency because the network's not executing for you anymore. You're executing now. And of course, as we've said many times, there's no privacy in the account model. And in this particular case, I did convince you that there's data privacy, but there is no account privacy. And so everyone can see how frequently you're interacting with this program. And you can imagine that, in terms of business, this is a huge league of knowing, like, oh, competitor A had, 25, had this person go 25 times, I should go after this person, try to convince them to come over to my business. Or you could also think about it as snooping on other people and saying, I'm curious what applications they're using and how frequently they're using it. I can just look at that data. And so account privacy is still not available in this model. And so to kind of break down and summarize the properties that we just established and we just established don't work, we said, first off, there's no more ledger executions, which is correct because we're using zero knowledge proofs now, and the proofs themselves attest to the transition. We also said that there's now data privacy because we're committing to balances and we're encrypting storage state. We just established there's no account privacy because addresses cannot be encrypted. They are fundamentally how we index into global state in the account model. It is in the name itself, the account model, that you index via your address. And so there is no account privacy there. We also said that, just like in that concurrency argument, we have to consume the entire program state in order to update it. And so this is not an efficient state update. To give you a very kind of concrete analogy, if you take the ERC20 token contract, inside of there's a mapping. It's a mapping of address to balances, right, in 64s. And what we're saying is, for all of these key value pairs of addresses to their balances, we're going to take all of them, put them all into the program. We're going to prove that the new state is just the identity function for every entry, except for my entry where I'm decrementing by some amount, and the receiver's entry by incrementing by some amount, the same amount, and proving that that part there, value is conserved. We're basically performing this type of a state update, which is incredibly cumbersome, as you can imagine. And so this is not an efficient state update for a zero knowledge proof. And of course, for the exact same reason, this means that there is no concurrency, because once I've updated my ERC20 entries, this other guy who took the same state at the same time can't update theirs because they technically need to use mine in order to linearize this. And so this is a sequential issue, as you can imagine. And so you may ask, well, how do we solve these things? How do we address account privacy? How do we get some efficient state updates? And how do we introduce concurrency? Well, we propose something called the record model. The record model is effectively a further abstraction and encapsulation of global state. To give you concretely what this looks like, in this model, we still have users with addresses who are going to create transactions, but now instead of having the transaction just say, hey, please run this application on this input, here's my signature, we're going to actually execute the transaction ourselves locally on a set of records. And in the transaction, provide these transitions with proof saying, here, I executed these records correctly. And when the network updates it, the program itself no longer is just a global store of encrypted state. It is now an abstraction over records, where every record has its own ID. It's a commitment in this case. And we can use that to look up individual records. So we've effectively slotted or split up that state in a very structured format. And because of that, this opens the door for us to now perform efficient state updates to abstract away the address so the account can't be leaked and introduce concurrency at the same time. And what I'm going to convince you of in the next few slides is to show you that concurrency actually is achieved in this model, and that we can prevent double spends, which is frankly a dual of the concurrency argument here if you can solve it correctly. So if we go back to the statement that we were looking at just previously with regards to proofs, we said, given some code, the predicate code, which is the same here, we're going to execute some old state. Now, instead of just the state itself, meaning the balance and the storage, we're now actually going to provide you records. And so with these records, we're going to provide the old records, and then we're going to claim, hey, there's some new records. And with that, we're going to check, just as before, that the value is conserved. Now we're going to access the balance from the records themselves. And so we're going to open those, and we're going to check that the sums on them equate out, so that we're not minting money out of thin air. And we're also going to take the program predicate and execute that by opening it and then performing the execution. And so this will, again, provide a guarantee that the assignment is satisfied for this construct. And with that, if this works, then the network can accept and admit these transitions and effectively perform global state updates on chain. Now, to give you kind of a sense on this, so going back to properties, the account privacy concept is achieved now because we are including the address of the owner as an encrypted piece of data inside of each record. And so the record itself no longer is an index via your address. And so by abstracting that one layer down, we're hiding the actual account data inside of the record, and we can just pull up records, and you can pull up records for your state. In terms of efficient updates, if we go back to that ERC20 example, the easiest way to think about it is to say, when we go into that mapping, the entry of accounts to balances, we don't have to take every single entry anymore. If every entry is just a record, we can just pull up the record that's ours and the record for the receiver, or we could even create a new record for the receiver, and we can say, here's my record. I am going to perform my state update on this, and I'm going to subsequently issue out this updated record for myself as well as the receiver. And that gives you the ability to just touch the entries in the program that belong to you and the relevant person without needing to actually reason over everybody else's entries in here. And so this record abstraction is fundamentally giving you the ability to segment or compartmentalize your information from others. And this then allows you to then say on chain, well, we have a Merkle tree of all these leaves. Leaves are usually the entries. Now concurrency is achieved. Why? Because we can have the network effectively take all these record updates and then in one go update a Merkle tree with everybody's deltas, everybody's diffs, and then subsequently linearize that and patch up to a Merkle root and put that into the block header. And so this fundamentally gives us the ability to get back the feature that we had in the previous account model, now in this record model, but with concurrency. So hopefully that helps to give you some intuition on the design that we're talking about here. For the next part here, I really want to get into showing you what we've built and how we've designed Aleo to actually function. So let's jump right into things. The first is that for cryptographers in the room, we've built our system on BLS 12377. And we chose this curve because it is pairing friendly. So that implies fast proof verification. And underneath that, we've done a twisted Edwards curve. And with the twisted Edwards curve, we've chosen this because it offers efficient cryptographic primitives. Things like Peterson hashes or commitments can be executed very performantly on this curve. For the snark, we are using Marlin, which was published in Eurocrypt 2020. And Marlin itself runs on BLS 12377 here. It's based on BLS 12377. And Marlin is a universal and updatable snark, which is, for us, great because we want to offer the ability for developers to just deploy their program without having to reason over setup ceremonies that you guys may be familiar with. And so with that, we've built up this model where we introduced this language. It's called Leo. Leo is a very high level syntax. It looks and feels a little like TypeScript or Rust. I'll show you that in just a minute. We then have this execute on a prover, which you can run yourself. It can be a binary as well as a hosted service, kind of depends on your computing needs. And then lastly, deployed on chain. And it's finalized and settled into blocks. In terms of what we've offered under the hood in terms of that architecture is that we start from Leo, we actually compile it down into what we call Aleo instructions. And then from Aleo instructions, we then serialize it into bytecode, which is what's hosted on chain. Let me walk you through an example of this. Let's start with Leo code. So here's an example of some Leo code. This is a very basic hello world. As you can see, we define a program with a scope called hello.aleo. We can then have a transition. The transition here, we just call it main. It takes as input a public variable X, which is a U64, as well as a private variable Y. It's private by default here, which is also U64. And we expect to output a U64. In terms of line 3 and 4, we are multiplying X and Y into Z, and then we subsequently return Z. Hope that gives you a little bit of a taste. Under the hood, Leo supports 16 different data types. There's algebraic ones, binary, data types, integer types. So there's all sorts of stuff. And then additionally, we also offer custom types, which is typically expected now. So we have structs as well as records, records being just what you saw in the previous few slides. And here's an example of what a struct looks like. So we have here a message. It contains a timestamp, some amount, and a signature. A signature here could just be another struct, basically. We also have a record type, which itself contains a record called token, which has an owner. It has some gates, which is the lowest denomination of credits, Aleo credits, which is the base currency here. And then L4 shows the amount, which is for the token, how much of this token is there. And just to show you the composability, you can also combine records and struct types. And so we can have a payload that's just a struct. It contains maybe the amount and timestamp and a ticker. This is like a nice abstraction layer potentially. And then you can have some record, which is holding state. And in this model here, we have a piece of message that is itself the payload. And so there's kind of ways to black box that and layer it further so that you have better abstraction. Let's dive into what Aleo instructions look like next. And so if we take that same piece of Leo code, this hello.aleo, converting this into Aleo instructions would look like this. So under the hood, Aleo instructions looks and feels a lot like assembly for those who are familiar. And so here's, we have function main. Now we have input register 0, which is a public U64, and input register 1, which has a private U64. We then say, let's multiply register 0 and register 1 into register 2, and then output register 2 as a U64 private. And some of you may be saying, wow, that has like some very strict typing on this level. And I'd say yes, for snarks, it's a very important aspect of defining the construct and also making your construct safe. Sometimes I kind of say this is a little CUDA-like in that sense, but in any case, this is what the syntax for Aleo instructions look like. And in practice, I think most developers will write code on the Leo level because it's more abstracted, it's a little easier, more familiar language and syntax. But certainly for those who are cryptographers who really like to count their constraints, I think they would likely end up actually enjoying using Aleo instructions because of how fine-grained it is. With Aleo instructions, we have opcodes that are for arithmetic and binary operations. We have assertion types, we have conditionals, we have comparators, commitments, as well as hash functions. And so there's a it's a small toolbox of, I think it's like 50 or 60 opcodes currently that contain kind of all the basic necessities that one would expect in order to write some programs here. And obviously we're always looking to introduce new features. So if there are ones that you'd like to contribute to, please feel free to check out our GitHub repos, which I'll link to at the end. But yeah, with that, once we have Aleo instructions, we then compile it down and serialize it into bytecode. And so let's show you what bytecode looks like. So if we take that same piece of Aleo instructions we just looked at, well, it's kind of what you'd expect. It's serialized hexadecimals, and this is kind of what we end up with. I think the important thing to call out, though, is that we've been very deliberate in ensuring there's a bijection between Aleo instructions and avian bytecode. So, and you may wonder, why is this important? Well, think about in the existing status quo, if you deploy a smart contract onto Ethereum, one of the challenges is that unless you go to Etherscan and the deployer actually put up their original smart contract code, it's very hard to decompile Solidity bytecode. And so it's very hard to immediately garner without like ABIs and inference, what this program is doing. And in this model, this at least takes you to some assembly level language, which is much easier to parse. And then from there, you can easily decompile it back into Leo. Obviously, you'd lose variables along the way, but you at least can pretty clearly see what the logic is doing, and it maintains this functional style of code organization. And so it should give you a far better kind of sense on what's happening. And I think this will help a lot in terms of clarity with on-chain functions to understand if this program is risky or not to execute or run. And the ambiguity in existing L1s has created vulnerabilities in the past. All right, let's jump into, let me do a quick demo just to kind of show you this, what I just showed you concretely on my screen, and then we'll take it towards the end. So I have here a program, which is tic-tac-toe. And you can see here that tic-tac-toe, in case for those who aren't familiar, it's a 3x3 grid. You have 2 players, one player places X's, the other places circles. Here we have a struct called the row. Row here has column 1, column 2, and column 3, which we represent as a U8. I believe we say 1 is X and 2 is a circle. And we see that a board is just a composition of 3 rows. And so we have row 1, row 2, and row 3. We can initialize a new board by calling transition new, and this would give you a new board. We have here function check for win, which is doing a fairly straightforward horizontal, vertical, or diagonal 3 in a row check. And we finally have this make move function, which is the kind of core part of the operation. So this is what you would typically as a player call to say, here's my row and my column and the state of the board. It can basically go through the entries, update state to make sure that the new values are reflected. It creates the new board. This is the updated board that is to be returned. And then additionally, we call that check for win function that we just saw here, which is the horizontal, vertical, and diagonals. And we say, sorry about that. We say if the win is true for 1 or for 2, then we will return the updated state with the winner. Otherwise, we just return continue. And so this is what this looks like. Now let me execute this for you. So let's watch the gameplay happen. Let me make this just a little bigger for everybody. So we have here, and I've added these visuals to make it a little easier to track gameplay. So here, and just for context, this is running on a MacBook Air at the moment. So this is us calling tic-tac-toe. We're calling that new function. Remember, that was to return a new board. So we return a new board. It's all zeros. Then we say player 1 makes the first move. And in 2 seconds, we made the move. So this was that make move, that main function that you just saw. It's 856 constraints. And you can see we just made a move in the upper left corner. And so there's a 1 right here. Now we go, player 2 makes the second move. Again, 2 seconds, 856 constraints. You see there's a 2 right here now, and it's in that center. Oh, sorry, yeah, 2's here, which is in that center position. And then we subsequently follow up with player 1 making the third move, which is now down here. Then we have player 2 making the fourth move, and fifth and sixth, and I'll just let this finish off. We now have player 2 making the sixth move. And I think one thing to call is just that this model that you're seeing here is a developer environment. So you're running, or we're running this locally, and it's easily adaptable into other formats. And so one of the cool things about this design is that you could, in theory, actually execute this fully off chain with both players. Like you can have both players put some amount. If you want to make it like a bet, you can have both parties lock some amount of tokens on chain, and then subsequently off chain execute those moves. All these make moves in sequence, and then at the end have either party or both post the final results of these iterations of transitions as one transaction, and claim the bet, for example. And so there's many ways to kind of think through this design, but hopefully this gives you kind of a concept in terms of how a game like this can work. I think lastly, I'll also show you just a quick, much more elaborate version called Battleship. Battleship, for those who are familiar or who aren't familiar, there's 4 pieces. So you have the battleship, which has carrier, a cruiser, and a destroyer. With that, we want to basically first validate that the ships are valid ships. And with that, we also have this transition, which is to offer battleship. So this is how you can move game state back and forth. And then you can also start battleship, which is to actually start the game. And so effectively what the players are doing is keeping an encryption of their board state on one side, and then the other party is encrypting their board state to their address. And each side has encrypted boards, but only under their own view. And you're passing these boards back and forth in order to play this game of battleship. That gameplay is here with this play function. So you have a move. The opponent will typically, encrypt and sign this move, which then gets passed over. And then you're obligated to take that move, which is encrypted under your address, decrypt it, and then subsequently actually parse the move and play the move based on the logic defined here. And so this allows you to actually get like a sequential iteration of gameplay where you can check if it is hit or next move. Playing this out takes quite a long time, so I'll skip running it, but just know that this is a public GitHub repo. I'll show you in just a second here, and you can try running these yourself. Just for the sake of time, I just want to say Aleo is proudly written in Rust. It's open sourced, 40+ contributors, 65,000 lines of code. You can find us on GitHub. I'll show you the GitHub right after this. We currently are on testnet 3. Testnet 3 is live. For those who are interested, you can go check out developer.aleo.org. And this is the workshop repo that I'm mentioning. So if you go to github.com/aleohq/workshop, you can find this example that I had right here. In fact, there's quite a few examples. My slides will let me. So we have here a auction, a basic bank, battleship, tic-tac-toe, a token example, as well as a vote contract. And there's also installation instructions. So if you just run this install script here, install.sh, it'll allow you to install your stuff it'll install Aleo and Leo right off the bat. We also have IDE support for VS Code, Sublime Text, and IntelliJ. Yeah, like the walkthroughs are available if you just CD into any of these and just hit run on those. And so I encourage you to check them out. Lastly, let me just finish up here. You can find us on Twitter at AleoHQ, as well as our Discord, which is aleo.org/discord. And with that, I will conclude and say thank you for your attention and thank you for your time. I'll answer some questions now.
Hey, thanks, Howard. That was a great talk. We already have. So we had 2 questions during the talk, and I tried answering them. Yeah, I think they were just about like people were confused. Like someone was confused about how it seems to them that it's an account privacy issue. Like the first strawman that you drew with like encryptions and commitments, and they were wondering how that prevents concurrency. To which I said that it's a global state. And that is the problem, that since you have a global state, that's causing the concurrency problem. And if you start fragmenting it, then you start going towards what you have done.
Yeah, so yeah, like in the strawman, one of the challenges is that, remember that in most blockchain protocols, storage state is Merkleized. And so in order to actually update the state, you're also claiming a specific Merkle root that you're transitioning to. And the problem is that if your history is not sequenced, then having multiple parties update that same state, they're going to start with the same Merkle root, but end up with a different new Merkle root each time for each of them, since they're all starting kind of from the same place. And so the challenge there is that you actually need someone on chain to coordinate all these parties' interactions in one go. And so what we did was to say, well, why don't we abstract each of those leaves, which is the actual entries of that mapping, into their own cryptographic structs, and allow for the network to then take those updates and Merkleize them in one go. And so, by abstracting this kind of one further down and providing these kind of records or these slots, so to speak, you actually enable people to kind of abstract there. And the pitfall of the account model design is to say, like, you basically you could in theory do the concurrency thing, but you would need an on-chain sequencer, and there's a central point of failure there. You're relying on this one party to effectively take everybody's updates and then perform this ZK update in one go, so that all the other nodes don't have to re-execute and check. So, like, I think for that person who's asking the question, they are right in a sense that if you wanted to do it in one go in that old model, you could. It's still very expensive because, if there's 1 million people in this ERC20 contract, and there's only 100 people who are updating it in this one block, you still have to prove the identity function for the rest of the entries, which is still not efficient. And so, I would say that you do achieve concurrency in that model, but you don't achieve account privacy or efficient state updates still.
Mm-hmm. Yeah, makes sense. So otherwise, so I think that was the big question. Otherwise, like, there's just some fan of yours in the chat.
That's nice. I appreciate it.
Yeah, let's wait for more questions. So I guess, like, one question that people might have, so yeah, like, I guess you already mentioned this, that for the hackathon track, they could look at these examples, and that would be a good place to start building new games, right?
Yeah, absolutely. I would encourage folks to check out this this workshop repo. It's just aleohq/workshop. With that, there's an install script that will get you all the very basics, so it'll get you kind of off the bat running with the command line tools that you'll need. And then subsequently, for your editor, your IDE of choice, we have plugins that you can then install there as well. And so, like, this code example here, what I have is using this Leo plugin, which you can also run code in, and it gives you syntax highlighting and kind of all the basic analysis to try to help you out. So that's certainly for the hackathon, what I would encourage you to start with. And then in addition to that, there is also let me see here. There's also this. So on developer.aleo.org, which I linked to in the slides, there is a deploy and execute demo. So for those who are interested to try this out on chain, we have all the steps here in terms of listing and, like, executing. So what I showed you there was a local execution on my machine, but you could also execute this and then settle on chain and continue to execute. And for that, you're going to need some tokens. And so we have a faucet that you can go to get testnet tokens with, and then from there you can then create your application and follow these steps to effectively execute and then and deploy your program on chain. And so this is kind of that model which we provide documentation for as well.
Okay, yeah, that's great. There's another question. So anonymous attendees asking, is the consensus mechanism different as well in Aleo?
That's a great question. So consensus itself fundamentally is subtly different in the sense that for those who are interested in thinking through MEV, we do have a unique kind of like realm of how you think through that, because in traditional L1s, the validators in consensus can see all the data. And so consensus itself can reason over the programs quite intimately. They can also order programs to be more financially favorable. In this model, the developer can choose how public they want the application to be. As you saw, we have visibility keywords, so you can make stuff public or keep stuff private. And with that, MEV it's a spectrum now. It depends on what you can see on chain versus what you can't see. And so this changes fundamentally the kind of interaction or the behavior that validators may go through if they're trying to financially benefit themselves.
Mm-hmm.
I see this other question here too about what is zero knowledge about tic-tac-toe? Yeah, it's a phenomenal question. So I think that there's a universe of what I call information symmetric and information asymmetric games. Tic-tac-toe is an information symmetric game. It's like chess. All players can see the board, And that's a game that's easily replicable on Ethereum. And so, to your argument, for information symmetric games, I'd say there's nothing zero knowledge in that sense about the tic-tac-toe part. But what is interesting is that we do leverage the computational integrity properties of zero knowledge proofs to give you the ability to do off-chain executions. And so unlike in the tic-tac-toe or chess game in Ethereum, where the players are both forced to play it on-chain and take turns waiting for block confirmations on-chain, this model can let you play in real time, fully off-chain. And so you can sequence the actual game via either a peer-to-peer protocol or a central or distributed server, doesn't matter. But the point is that you can go off-chain, play the game in sequence with all these proofs, roll up all these transitions into one transaction, and then publish that state on-chain. And so this gives you compaction, which is a very nice kind of design paradigm. If you think about games like poker, where there is a concept of zero knowledge, but there's also this real-time off-chain interaction, you can have a dealer actually deal out like 9 players and then ask them, check or bet, maybe the first guy calls, and then it can subsequently for the rest of the players say call or fold, call or fold, call or fold. And you can have all these transitions bundled into one transaction and then broadcast on chain. And so that leverages the property of computational integrity in this design. And so that's for information symmetric games. For information asymmetric games like Battleship, which I showed, it's kind of naturally motivated. It says, player A doesn't want to see player B's board. Player B's board shouldn't be able to see player A's board either. This is where in the Ethereum model, you're forced into a commit and reveal scheme, which is even further laborious in terms of block confirmations, because instead of just waiting one confirmation for your opponent to play in order for you to play your next move, you now have to wait at least 2 blocks, assuming optimal transmission, to first commit, then reveal. And so, this introduces a lot of friction for gameplay. And we think that this is kind of fundamentally one of the nice properties of zero knowledge, is being able to kind of leverage the privacy aspects, but also in a real-time fashion.
Okay. So I have a question of my own. So the record model, it's great for a concurrency and also privacy, like you mentioned, but are there any limitations in terms of expressiveness, or just how hard it is to develop an application in this model?
Yeah, that's a really good question. There are absolutely challenges and limitations. There's also, I would say, opportunities. So for one, as you may be aware of, for loops, while loops, recursion, iteration, these are complex concepts to develop a compiler that can synthesize zero knowledge circuits for. And we've done at least our fair share on introducing for loops, if conditional statements, adding bounded recursion, but everything has to be quantifiable in this sense. And so there's a Turing decidability that is kind of part of this nature. There's now this concept of recursive proofs, which further allow you to kind of further iterate, and we see that as well as a batch execution. So you can split up a circuit into multiple pieces and kind of execute that in aggregate. And so there are kind of new techniques to make that much more efficient. But I'd say this is probably one of the main limitations of the design here, is the expressivity of that. I'd say, in the kind of L1 smart contract realm, it's not so much of a limitation, because most programs are fairly bounded. And in fact, they're incredibly bounded, and they're very limited in their runtime. We're talking about under 100 millisecond time slices that you can execute, since it's effectively like a mainframe today. And so from that perspective, I don't think this is a fundamental limitation, but it's certainly there. I'd say that the benefit of this design, of course, is now you can also scale it up fairly arbitrarily. That, in the Ethereum model, I can only execute for, that 10 milliseconds or 100 milliseconds I really pay up in gas. In this model, I could design even a roll-up application that is ZK and subsequently batch and fill, 10,000 people stuff, and just have it be one confirmation on chain. And so, there is a ability to now execute kind of arbitrarily long periods of time, whereas existing L1s limit how long you can execute for.
Mm-hmm. So that's one aspect of it. So I was thinking more in terms of shared state. So in that case, do you expect that like all the people who are involved in that state would come together and then create a transaction collaboratively, or is there a nicer way to handle that?
That's a great question. So let me just show you an example of that so that you can see. We have on-chain state as well as off-chain state or executions. Like there's records off-chain, and then there's like your standard like mappings and data structures on-chain. And so if we take a look at like a token contract, we actually kind of iterated through various designs. So we have like an on-chain storage, which is like your mapping of account from address to balance. And then we also have a concept of an off-chain record for your token, which has the address as the owner and the amount as the balance here. And so, you know, when you're say, let's take a look at transferring, you could transfer it publicly. So this transfer call actually just it just directly calls the finalize scope, which is this scope right here. And finalize is actually on-chain native executions. And so this here says, let's decrement the senders by the amount, and let's increment the receiver by the amount. Unlike in Ethereum or kind of existing L1s, all math here is safe math by default. And so this function will immediately halt if an underflow and overflow happens. And so it's kind of one of the nice things of, you know, having the hindsight now or foresight, having seen existing design paradigms. And here's a private version of that. So the same transfer function, but if you want to do it privately, you first compute the change for yourself, and then you mint two records. One is a token record with your remaining change, and so that's the difference. And then the other is for the receiver. It's a record that says how much you've transferred with the amount there, and then now you just return two records. And so you can see the function signature here returns two token records. And so this gives you a way to do it in a zero knowledge context, purely off chain. But you can do it in either one. And so for the concurrency and kind of for the on-chain liveness, like we do have this concept which allows you to update state. So like if you're in Uniswap and you need to update like some global reserve A and some global reserve B, you need to decrement and increment here, you can have this be done in consensus several times over many transactions in one block.
Yeah, that makes sense. Yeah, thanks for answering all the questions. I think we are near the end of the session. And yeah, if there are any other questions, feel free to ask them on Discord. Yeah, I can try answering them, or I can relay them to Howard so that he can answer them. And yeah, so I don't think we have any other questions. For the Berkeley students joining, please join me in the on the other Zoom session where we'll be having the discussion section. So that's it. Let's thank our speaker Howard again, and yeah, hey, have a nice evening.
Thank you very much. Thank you, everyone.